exponential equations. It's one of the reasons we have logarithms, or not why we have them, but one of the reasons they're useful, I suppose. It's probably a better way of saying it. So we get an equation like this, but the pronumeral we're trying to find is in the power. That's fine if I can rewrite that number as 5 to the power of something, and in this case I can. So I know straight away, well, x is 3 because 5 cubed is 125. Not an issue. I get something like this. Well, even this is achievable because I can rewrite both sides as 2 to the power of something. Because 4 is, of course, 2 squared. And then on the right-hand side, we have 2 to the power of negative 3 on 2. So therefore, I know that 4x plus 2 is negative 3 on 2. X ends up being negative 7 on 8. Terrific. But sometimes we need this little one. It's called the change of base formula. So when it's in a base that's not useful, I can change the base of what I'm playing with. So if I want to change the base of a logarithm, so currently if I'm working with base A, but I'd prefer to be working with base B, then I just rewrite it as, okay, I'll make it base B. But then you have to divide by the logarithm of the old base. Okay. So 7 to the power of x equals 32. This is where we have a problem. Because 32, 7 to the power of what? I mean, there's not a nice, neat number that's going to work there. So we log both sides. Now, at this stage, that log is base 7. So that doesn't really help me. Because the calculator that I'm going to use for this is base 10 or base E. So I need to change the base to one of those. Now, it doesn't matter which one I change it to. I probably changed it to base 10, did I? Oh, I didn't even bother writing the base down, so there you go. So it'll be log of 32 divided by the log of the old base. Now I can go to my calculator and work that one out. So as I say, it doesn't matter which log button you use, just make sure you use the same one for both calculations. So 3 to the power of x is 5 to the power of x minus 2. Okay, I'll log both sides. Again, I haven't bothered with a base here. It could be base 10, it could be base E. I mean, they're the two buttons I've got on the calculator to use. Again, as long as I use the same one. We had a log law that said we can bring those powers to the front of the logs. So x log 3 would be x minus 2 log 5. Now I can rearrange all that and make x the subject. So this time I get 2 log 5 over log 5 minus log 3. Now I can go to my calculator and get an approximation. And again, it doesn't matter whether you use the log button, LOG, or whether you use the natural log button, the LN, as long as you use the same one in the one calculation. And we'll get 6.301. This is actually a quadratic equation. You might not see it straight away. But if I think of the pronumeral as 3 to the power of x, right? So if you like, I'll give it a different pronumeral if you like that. M is 3 to the power of x. Well, that means m squared is actually 9 to the power of x. Once I play around with the indices there, you can see we get 9 to the power of x. So I've really got a quadratic equation, m squared minus 4m plus 3. So I can solve that like normal, and we get m equals 3 or m equals 1. But remember, that's m. That's not what we're trying to find. We're trying to find x. And we said m was 3 to the power of x. So 3 to the power of x is 3, or 3 to the power of x is 1. And those ones I don't need to change the base, because of course 3 is 3 to the power of 1, and 1 is 3 to the power of 0. So I know that x is 1, or x is 0 for that particular one. Now, whilst I went through all this effort of changing the m squared to 9 to the power of x, in the actual equation, just look at the base. 9 is 3 squared. So if you notice that one base is the other base squared, then you can, oh yeah, we can probably turn this into a quadratic equation. What about inequations though? We don't see these a lot. But what happens with them? Well, the exponential curve, and the log curve for that matter, is continually increasing. Okay? It never decreases, the basic one. So because of that, when we take the inverse of each side, that the inequality will be preserved. So if I have to solve something like this, 2 to the power of x is in between 1 and 32. I can log all three things and the inequality will be preserved. Now I've logged it base 2, and so log of 1, well that's always equal to 0. Log of 2 to the power of x base 2, well that's just going to be x, because I could bring the x to the front and then we'd have log 2 base 2, and we said that was equal to 1. And log of 2 to the power, log of 32 base 2, we're saying 2 to the power of what's 32? Oh, well 2 to the power of 5 is 32. And then we can solve that inequation or inequality. So a log 1, if I'm saying the log of x is greater than 2, then I could exponentialize, if there is such a word, exponentialize both sides. So this time it's base 3 we're dealing with, so I'll make both sides base 3, and I get 3 to the power of log x base 3 is greater than 3 squared. But remember we said 3 to the power of log cancels. I mean that's the whole point of exponentializing it, if you like, because basically we're saying we want to cancel the log 3. And I end up with x is greater than 3 squared, x is greater than 9. So exponentials and logs with inequations are quite easy, because we can still just do the inverse operation and the inequality will stay fine. Okay, so that's 8B.